Okay. Thank you all for coming today. We have a colloquium presentation from our quantum computing group. They are working on a hybrid quantum classical project to generate candidate molecules for to see if they can be built, and they are running a verifier that verifies if the molecule is a buildable molecule using computational methods. I'm going to go ahead and turn it over to Diptanshu, who can explain in detail how it all works.
Thank you, Dr. McMahon, for that introduction. Let me try to get this thing to work. How does it look for you?
It looks very good.
Okay. So hello everyone, I'm Diptanshu Siddhar, and today we will be giving you a short presentation on our work. It's a hybrid quantum classical generative adversarial network for generating chemically stable molecules. So this project we have been doing for over 2 semesters. So we do have Max, Adelina, Arjun, Satvik, and Kanti for this semester. And last semester we welcomed Joey Huang. And our advisor is Dr. Larry McMahon. So let's get started. So a fancy title, but what are we researching exactly? So first I want to talk a little bit about the generative adversarial network, which is an unsupervised learning algorithm. It works efficiently with complex and or missing data. And what I mean by missing data is essentially if you have a data set, but you don't have all the scenarios in the data set. So suppose maybe you were talking about different age groups and we don't have a certain, like the older age group. Maybe we have the younger, but not the older. So that would be sort of missing data or things like that of that sort. The generative adversarial network can still learn, can still generalize. So that's one of the good aspects of the algorithm. But it doesn't come with its own share of problems. And one of them is the vanishing gradient problem, and the other is an increasing time complexity. Now, of course, GANs do have applications, many applications, and one of them is chemistry. And in chemistry, so we have the option to actually build molecules in the lab, which can be expensive. It depends on how many molecules you are trying to build and how many combinations you have to get through before you can get an actual candidate that you can then explore further upon. And so there's the MolGAN, which we have found as the only significant breakthrough, because they have aimed, the people behind the MolGAN, they have aimed to make a computational model that learns from all the molecules that that are there from this, like whatever data set that they have, and they use that to build some molecules or generate some molecules that are chemically stable. So but they are obviously classical process, and we wanted to speed that process up, maybe because we're quantum computing, so maybe combine machine learning and quantum computing and see if there's any sort of speed up that we can get. And so the goal of this project was to develop a generative model to create valid molecules more efficiently than classical machine learning models.
One question. Before you go on, can you explain the vanishing gradient problem in a little more detail so that people know? I think we understand increasing time complexity, but that's the one thing on this slide that's hasn't been described.
Sure. So vanishing gradient is essentially when we're talking about, say, optimizing your function, right? So there you have to calculate the gradient, and so the mathematical gradient, that is, And suppose you're on a certain, like, if you imagine like a 3D landscape, and you are say on the top of a hill or at the very bottom of a valley where there's like a local minima, right? And you calculate the gradient there. So your gradient, it would be like so shallow, it would be like so small, it's close to zero, that your there's no like adjustment that can be done or is done to your parameters within the model. So while it's optimizing or training, we have to tune the parameters within the the model, but it doesn't train because of this sort of this problem, right? It's a small it's a very small slope, so it just stays the same. So we end up keep doing iterations, keep trying to train the model, but it doesn't train. So that's essentially the vanishing gradient. And there are ways to fix it. There are ways to fix it using like there's certain optimization functions that you can use, optimizers that is, and activation functions as well.
Thank you.
Okay, so next, Max will give an overview of how do GANs actually work.
Okay, so GANs are short for Generative Adversarial Networks, and they are a machine learning algorithm where two networks compete against each other to facilitate the production of an object. So for example, image generation. The two components of a GAN are a generator and a discriminator. What these two networks do can be described by the image to the right. Essentially, the generator is like a fraudster trying to manufacture counterfeit money, while the discriminator is a detective who is trained to classify sample money as legit or counterfeit. Now, because of this architecture, GANs have a unique training process in order to simultaneously train both networks to produce these objects. We'll elaborate later when we get to our step-by-step overview of our QGAN, but for now, in each epoch, the generator basically learns how to generate more realistic objects, and the discriminator learns how to discriminate better against real and fake. Okay, this repeats until the generator and discriminator are close to a 50-50, meaning that neither network can gain a significant advantage over the other. So the generator can't like generate better objects that fool the discriminator, and the discriminator can't like become so good at discriminating objects that it makes the generator have to like adapt itself to get better.
So as Dipanshu mentioned before, there is like one application in the GAN that has been used in chemistry, which is called the mole GAN. And this application essentially generates synthetic and chemically stable molecules. So we were wondering whether quantum computing would provide a speed up. So quantum computing is basically leverages like the quantum properties such as superposition and entanglement to speed up classical computing. So for example, it can process high dimensional data very efficiently, and it can also store data exponentially higher than classical computing. So because of this, quantum computing is typically much faster than classical computing. And so we proposed making a quantum version of the mole GAN. So in our quantum GAN, we decided that we would have a quantum generator and a classical discriminator. And essentially, the quantum generator would use the properties such as superposition and entanglement to generate random numbers. And then the discriminator would be similar to a typical neural network, and it would differentiate between real and fake. And for our quantum generative adversarial network, we would train it on the QM9 data set, which we will elaborate on more later, but it consists of about 100,000 small organic molecules in the XYZ representation.
Great, thanks. So now we'll get into the nitty-gritty of the QGAN itself. So how does the overall methodology work? So of course we have done the quantum generator and a classical discriminator as the main like component that we have contributed to the quantum GAN itself. But here's like a flow chart that shows what's going in, what's coming out, and how is the training loop. So starting with the data set, yes, we're using the QM9 data set, and as Adelina has stated, it has molecules in the XYZ file format. We have then converted it into the CSV, which is easier to use in our classical discriminator. We have also implemented the post-generator processing here. QADC stands for Quantum Analog to Digital Converter, and I will talk about that in a couple of slides. And then finally, we have the discriminator, which, as Max has iterated before, checks whether the given sample is real or fake, whether it has come from the generator or it has come from the data set. And so here's the indicated training loop. So the discriminator has to train, but the discriminator also provides values that help train the quantum generator.
So as I said before, we used the QM9 dataset to train our QGAN, which has approximately 134,000 organic molecules, which has up to 9 heavy atoms. And the term heavy simply just refers to any non-hydrogen atom. And specifically in our case, it has the atoms of carbon, nitrogen, oxygen, and fluorine. So we originally tried to use the simplified molecular input line entry system or the SMILES representation method to encode the molecules. And essentially this is a string representation of molecules. So it would encode the several molecules, the molecules as spatial features, but this representation method typically faces issues in machine learning due to its complex grammar, especially when it comes to generative adversarial network, when it has to not only learn the grammar, but also generate new molecules or new instances with that specific grammar that fits the criteria. So in addition, this string, since this method uses strings, there would also be a variable length, meaning that it would be hard for our generator to generate similar molecules. So to mitigate this issue that we found, we decided to use the XYZ representation instead. So essentially, the XYZ format is a way to represent the molecular geometry of a molecule. So it would represent the 3D structures of the molecules by having the list of atoms of the specific molecule and in the form of an atom vector and its corresponding X, Y, and Z coordinates of each atom. So prior to passing these XYZ represented molecules, we decided that we would convert the file type from XYZ to CSV, which Divtansha had mentioned earlier. And all this means is simply changing the file extension on the files, and this would just make it so that it's easier for us to work with the data in Jupyter Notebook, which is what we use to code our entire quantum generative adversarial network. So our quantum generator essentially works by generating molecules that mimics the XYZ format by allocating specific sets of qubits for generating the respective parts of the XYZ format. For example, we have a set of qubits to generate the atoms, a set of qubits to generate the X coordinates, a set of qubits to generate the Y coordinates, and a set of qubits to generate the Z coordinates. In total, we utilized 19 qubits total with 1 extra, with 3 qubits per atom for 6 atom molecules and 4 to 6 qubits per atom for 48 atom molecules. In the future, however, we would like to utilize 32 qubits, but this is not currently possible due to the limitations of the quantum computers. So furthermore, after we generated our molecules, we had to find a method to validate and make sure that to find which ones were actually valid and which were not valid. So to do this, we actually converted from the XYZ format back to the smiles string representation. And this is because since the smiles representation follows a very specific grammar rule, set of grammar rules, for example, different types of bonds have different symbols, and parentheses are used to indicate like different branches in the molecule, and there are numbers to show different rings in the molecule. This means that any invalid molecule in the XYZ representation would not have a valid smile string to correspond to it. So as a result, if we were able to find out that a generated molecule we were not able to convert that and form a valid smile string, then that molecule would automatically be invalid.
Okay, so now onto our QGAN architecture. So as we've mentioned before, it features a quantum generator, which uses parameterized quantum circuits to help map inputs to outputs. So basically generating realistic molecules. These quantum circuits have trainable parameters, which in our case are rotation angles that can be adjusted to optimize the production of the molecules. So as Adelina has mentioned, because we use quantum computing here, we can take advantage of superposition to represent multiple states at once and entanglement to parallelize computations, making the generator much faster. And in addition, we also use the parameter shift optimization, which is just a super fast optimization algorithm for quantum computing. Now, after the generator comes the discriminator, which we decided on keeping classical. So opting for a hybrid quantum classical QGAN in the overall. Although there are QGANs that have like fully quantum discriminators, we felt that the discriminator didn't really need the speedups offered by quantum computing, since all it really does is classify between real and fake, which is arguably a much simpler job than the generator, which has to generate realistic molecules from scratch. And now finally, we have our output post-processing algorithms, which allows us to convert our data into formats that can be operated on in the quantum and classical domains. So we can switch back and forth between our generator and discriminator with ease.
Great. So we'll talk about the generator now in detail. So what comes into the generators? In other words, what is the input? Well, it may sound counterintuitive, but it's actually random noise, which comes from a uniform random distribution of numbers between 0 and 1. And the reason it takes random noise is that it's the original intent is supposed to, be able to take from a random distribution, decipher take just a sample out, random sample out, and have the right set of parameters tuned to the right set of rotational angles in this case, so that it can generate a molecule. And that's also why it generates different molecules every single time, because it's starting out with a different input. And so that's for the input. Now for what's going actually inside, well, we have mentioned we're using the entanglement, superposition, all those kind of quantum mechanical principles. But how do we do that? Well, we use a parameterized quantum circuit. Now, the beauty of a PQC is that we have these rotation gates, which, they're qubits, they can rotate different angles, and we can manipulate these angles, using these rotation gates. And we see I've written HEDMARD here. That's a gate that's used to do superposition. A CNOT, the controlled NOT gate, is used for quantum entanglement, and then the rotation gates, which have the trainable parameters. The output is measured on the Z basis, so it can either be 0 or 1. So essentially, the output of the generator is just a bit string of zeros and ones. And the last stage is basically the updates. How do you update the parameters within the PQC? Well, the decision comes from the classical discriminator, comes back to the generator, and then we do have the parameter shift optimization, which basically helps us to adjust the rotation angles accordingly. Now, remember I talked a little bit about the QADC before, and it's one of the it's a hallmark algorithm, at least the ADCL, analog to digital converter within like hardware designs for your regular classical computers. So I did try to take the inspiration and build it for quantum. And essentially its purpose is to convert a bit string into an XYZ file, which can then be ported into a CSV file very easily. So why do I need this? Well, as I explained in the generator, we're generating a bunch of, we're measuring like zeros and ones. We're generating a bit string. So this is sort of an example of what we would get out. So that has to mean a molecule. And so, yes, we have to transform it into 4 entries: the atom itself, what are we talking about, and the XYZ coordinates of the atom. Well, how does it work? Well, here's the mechanism. So we're starting with a bit string, maybe just take 10011 for example. In binary, if we convert that into decimal, this is 19. And we'll have a constant value here. Say it's 8. We can change this constant value depending on how much precision we want or how much range we want. So if we want like numbers from 0 to 7, maybe we'll get a smaller number, and then, or if we want sort of more precise, so more numbers after the decimal point, we might put a larger number to get more precision. And so we see it here, the magic is here. So we just divide, we do a division operation. 19 by 8 is 2.375, and this is one x, say the x coordinate of certain atom.
Okay, so finally we have the discriminator, which is the critic responsible for updating both itself and the generator as well. So first, as input, it trains itself on an example of a real molecule from our data set. So it knows outputs from the generator that don't closely resemble this will be fake, and vice versa. So here we also tell the discriminator the real label of this molecule so it knows. Next, we also feed the discriminator a generated molecule from the generator, but we actually don't tell the discriminator that the generated molecule is fake because the discriminator is supposed to classify this as real or fake based on the examples it was trained on. So here, the discriminator just returns 1 or 0, which represents real or fake respectively. After the discriminator tells us this, we then tell the discriminator that, by the way, that molecule we just gave you from the generator, it was actually fake. So if the discriminator was correct, we tell it, oh, you did a good job. You should classify more of those kinds of molecules as real, and vice versa if the discriminator was incorrect. This helps the discriminator better distinguish between real and fake examples of molecules. We also tell the generator the verdict of the discriminator, so the generator knows how to improve and generate more realistic molecules that will fool the discriminator. Okay, now on to our results. How exciting. Because our QGAN is unfortunately currently subjected to the RAM constraints of Google Colab, we can only generate medium-sized molecules with accuracy that is not what I would call high. Adding more qubits would allow us to generate more complex molecules with greater accuracy and realisticness, but this would increase the RAM by a lot, and we wouldn't be able to use Google Colab, so we'd have to run on the ASDRP server, which is something we're planning on doing. So as of right now, we've generated around 300 molecules, of which 7 are sufficiently accurate. So what that means is basically like the atoms in the molecule are accurate, but not their coordinates, because that requires more bigger range and precision in the analog to digital converter. So you can see some of the examples of what we've generated on the right. Now, both of these molecules actually exist. And on the bottom, you can see our generator and discriminator loss for your own interpretation.
So in conclusion, QGANs can provide a stable convergence compared to like classical generative adversarial networks due to its ability to harness quantum properties. And yeah, furthermore, using a QGAN in the process of drug discovery can actually exponentially reduce the amount of time required to develop drugs. Because, for example, with because in drug discovery, typically like you start off with a bunch of potential candidates for targeting a specific disease, and instead of going through all of those potential candidates, by using a QGAN, you could test you could just test all the possible molecules that you want to do by pushing it into a data set and pushing it through your QGAN, and you can get like similar molecules which can possibly solve the issue that you're looking for. So a clearer instance of this would probably be like, for example, let's say you're trying to develop a drug that will target a specific protein in your body, and you know exactly like the specific properties that you need your potential drug to have in order to successfully fight off that protein, the target protein. Then you can just simply put together a bunch of drugs that you know, or molecules that you know in the past have worked on a specific similar protein. You can push that through the generator, the QGAN, and the QGAN can give you more similar molecules that can potentially target this issue. Furthermore, the applications of molecular generation also apply to a variety of fields in the healthcare industry, for example, with ointments, tablets, vaccines, and cures to other diseases. Furthermore, QGANs don't just have to be applied to chemistry. There are other fields that could also use a that could also potentially have a QGAN be applied to it. For example, cybersecurity, and one field that has already been using QGANs is with image generation and obviously image translation. So for us personally, a future project that we would be interested in working on is having a quantum discriminator, because as we talked about before, we currently use a classical discriminator. We will talk more about this in the next slide. Furthermore, we were also looking into having different data sets of molecules with specific chemical attributes. For example, we are currently looking into running our QGAN on this other data set called the Zinc 20 data set, and we're working with Mr. Downing to get that onto the ASDRP server because it's a lot bigger than the QM9 data set. In doing so, it would be a step closer to applying the QGAN to drug discovery. So over here, you can see the circuit layout of our generator, as well as the internal architecture of the discriminator. In the future, we might focus on tweaking out the layout of our generator to add or reduce parameters, as well as adding more depth and layers to the circuit. We would also focus on our discriminator architecture and making necessary changes. We will also consider a quantum discriminator.
Okay, first of all, we would like to acknowledge our research advisor, Dr. McMahon, for his guidance throughout this project. We would also like to acknowledge everyone in our group for their diligent work, great communication, and invaluable knowledge that has helped this project advance further over the semesters that it has been worked on.
We would also like to give a big thanks to Mr. New and Mr. Downing for their guidance and resources that they gave us to, better our project to make it progress. And finally, ASDRP for giving us the opportunity to conduct this high-level research. Here on the right is a QR code for our references. Please feel free to check it out. And thank you for listening. Hope you enjoyed it.
Okay, if anybody has questions, let's go ahead and ask the questions now. You can either unmute and speak up, or you can type in chat.
So I have a question. That was first of all, Larry, that was an awesome presentation. Here's a few questions. The first one is, in any sort of effort, we're always trying to balance, especially in chemistry, we're trying to balance cost versus benefit, right? For example, if you are going to come up with a virtual screening platform, there's obviously less material cost, but it's not zero cost. And it might give you some benefit in that it enables you to screen more compounds for less, cost. This may not be financial cost, but it could be cost in terms of time, resources, electricity, personnel, etc. How does this approach to molecular generation compare to existing ways of doing high throughput virtual screening? So if you talk to Harman Bratt and his group, they do a lot of virtual screening, but they don't generate their structures. They take these massive databases of commercially available materials or hypothetically commercially available materials from this library called Zinc, and they screen those through classical, docking type analyses. How does this compare in terms of cost versus success benefit?
Sure. That's a great question. So my take will be, so this, the QGAN itself, or the approach that we tried to go for was to, be able to have certain machine learning model, that is, to find out a molecule, potential molecules, possibly way ahead of time. That is, you give all kinds of, you may have some molecules following some sort of restraints. Hey, it has to have this property, this other property, so on and so forth. And, and you're trying to you have a specific goal in mind, but, there are many possibilities, and you're trying to narrow that, a volume of the space, the data space down into just a few molecules that you can then, experiment more on, right? And as for the cost and benefits, as you asked, so right now, since quantum computers are not, I would say, the best potential that they can be at, because we're still at noisy intermediate scale quantum computers, that is, we don't have that many qubits. We also make a lot of errors within in the quantum computers. And so right now there may not be a direct benefit that we can see right now, as of now. But in the future, when we get way more qubits, when we get access to way more qubits, when we lower the error rates using either error correction algorithms or just the materials of the quantum circuits themselves, basically once we get fully capable quantum computers, the benefit will come out that time. And this is just an algorithm that you can run at that point of time. Does that
that doesn't really answer my question. My question was more about, what is the benefit of this approach where you're generating structures based on, I guess one could say, rule sets, and based on rule sets that are subjected to neural networks, versus running high throughput virtual screens on existing, structural libraries?
So I am not,
right, because finding a hit compound is more than just a set of properties. If a molecule that works in a biological setting is just a set of properties, we'd have all diseases cured today. It's a fairly complex endeavor, and you can have a library of compounds that all have the same properties, physical properties, that might have different biological effects. An example that you might be familiar with is our amino acids, right? They're all, L amino acids, left-handed amino acids. Right-handed amino acids, which have the same chemical and physical properties, except for their rotation of plane polarized light, are extremely toxic to biological systems. Just the change of a single stereo center.
Yeah, so I think you definitely raise a good point there that it's not all about properties, but I think this algorithm is probably the first step towards it. It's not by no means it's like the only method and like a fully proof method for generating candidate molecules, but it's a tool that can help us to do so.
So I have a question for Edward, and that is,
Sure.
where do you get your library of structural compounds? It seems like this process could help generate the library.
Yeah, that's a good question. I think synthetic chemists tend to think based on hit structures. So the way that it's typically done is, people, not us synthetic chemists, but natural product isolationists have through the years sat there and isolated random things from plants and found that some are biologically active. That's where half of our cancer drugs from. Other times they come from design. So in other words, myself or another chemist or some students at ASDRP might sit down from a whiteboard and say, we want a molecule with these sorts of, functionalities at these positions. What starting materials are lying around that would enable us to get there in the fewest number of steps.
So you don't know when you do that whether it's a valid molecule yet or not.
Well, I think there are certain rules of thermodynamics that cannot be violated that a chemist would intuitively know. For example, a carbon atom bonded to 5 other carbon atoms, as a for example, would be chemically impermissible. Likewise, people have empirical evidence, and this is, a lot of this stuff is empirical, I should say, Larry. For example, if you have a fusion of 2 carbocycle rings, so imagine a molecule with 2 rings that are fused together. Those rings can be fused through the same side, it's called a cis fusion, or through opposite sides, a transfusion. It is chemically impossible to have a trans 3-6 fusion, for example, because 3-membered rings have an extremely high, strain energy, and this is all empirically derived, right? Likewise, an example of this would be, Baldwin's rules for ring closure reactions. There are a set of empirically derived and very much so verified rules for what reactions would be permissible in terms of ring closure events. So there are rule sets. It's just that these are typically empirically derived for chemists. So we rarely make a prediction of a molecule that simply cannot exist. I don't think that that's ever come to be the case where we think of a molecule and it's just impossible for this molecule to exist. I think what the bigger challenge that is typically had is, there's millions upon billions of molecules that could possibly exist. Each one is going to take, a year to make. Which one are we going to make?
Another thing that I would think is, if you have 5 molecules that you've recognized have a certain property, and it has that property in varying amounts, and that's the property you're interested in, can I generate an analog to any of these, or can I use any of these to generate a molecule that has the same property, only stronger?
I suppose you could.
I think that's where this one could make a difference.
Yeah, that's certainly. I mean, I think where this sort of stuff that you are all presenting really would make a difference is the quantity that one can screen in a given amount of time, right? So, yes. My group with synthesis, we can probably screen on a good week, maybe 50 compounds in a week. Right, Harman Bra, who does the more typical, molecular modeling type things, his group can maybe screen 150 to 300 compounds a week. If you can reduce the compute time per compound, you might be able to screen 1 million compounds per week or more.
Right.
But I think the question is a little bit more complex than properties, because you could have two compounds that have, and I guess it depends on how you define property. What's meant by a property? A physical property, a chemical property, biological property, even a chemical property. Are we talking about molecular geometry? Are we talking about positioning? These things are all very much so. It's a complicated realm with many variables, and I'm not sure that we can reduce it to a single metric. So that's kind of my 2 cents.
I don't think you look directly every time at the physical or chemical properties of the molecule, but you look at the reactions that you want it to create and say, do I get the right reaction byproduct if I use that molecule?
Right. No, that's accurate. And I would point you all in the direction, and I wonder, this is your competitive landscape. Millipore Sigma actually has an AI now called Cynthia, Synthia, that claims to be able to do retrosynthesis through AI. In other words, you give Cynthia, which is the software, a molecule, and you ask Cynthia how Cynthia would make it. And Cynthia uses AI to figure out how to make it, or how it would best be made. So that's another thought that you might look into. Yeah. Okay, I'm done talking.
Okay, there is another question in chat.
Max, you want to take that question? It says, how can you differentiate two different molecules that are very similar to each other when the error rate is more than 2%?
That's a good question, actually. I'll think about it and for a few seconds before I answer.
Sure.
Okay, I think even though the molecules are very similar, they will still have differences in the coordinates, X, Y, Z coordinates, even if it's just a few decimal numbers, a few digits after the decimal point. So the discriminator can still distinguish between the two. Yeah. I don't know, maybe the potential can add on.
Sure. I would just say at least the end goal is to make the discriminator so picky so that it picks up any, as Max said, some even small variations within the decimal points, right? We want to be able to be differentiating. We're focusing more on the precision, that is. So by focusing on the precision, we can even the error rate is large, we can still train the discriminator enough to check if this molecule is valid, or check this valid molecule whether it's real or fake. Any other?
Okay, do we have any other questions? Okay, thank you, Dipsachu. Thank you, Max. Thank you, Adelina. If anybody else talked in the thing, I'm not sure who all.
I've got one more question. This is for the guy with I think you've got a Canadian background or something. Is that Max?
Yes.
Yeah.
Are you from Canada?
Yes.
Or do you live in Canada?
Yes.
In Vancouver?
Yeah.
That's awesome. My one half of my family is from Canada, from Vancouver.
Oh, that's cool.
It's I haven't been there in a while, but I used to when I was in high school, we used to visit a lot, and I used to like to go on hikes and runs through Stanley Park, and sure you know where that is.
Yeah, I do that sometimes too.
Yeah, I got chased by a moose at Stanley Park when I was a sophomore in high school. That's a long time ago. So. Great, go Canucks.
Okay, thank you all very much, and we'll see you again next week.
Before you leave, I think there's one person who had their hand raised. I'm not sure if the person put it the question chat, but if you do have a question, please feel free to ask.
Okay, thank you very much. That was our colloquium for this week. You guys did a good job. Thank you. And we'll see you next week. And thank you, attendees. I hope you enjoyed the presentation.
Thank you everyone for coming.
Thank you.
Thank you. Great presentation.
Thank you.